Hi folks, and welcome back to Physics with Captain Rod. The purpose of this video is to go through some examples of how to calculate work. So remember in physics that work is force times distance. However, the force has to be parallel to the distance. So I'm going to go through a series of examples here. I'm going to go through 3 or 4 examples, and they're going to get progressively more complex. So I'm going to start here with example 1. A 20 Newton force is applied to this object, and it moves to the right here a distance of 10 meters. So work is force times distance. In this case, the force is 20 newtons. The distance is 10 meters. The force is parallel to the displacement. So there's no trig required or anything, and this force is in fact doing work. The work done is going to be 200 Newton meter or 200 joules. Now, the work is positive when the force and the direction of motion are the same. So this object's moving to the right. In this case, the force and the direction of motion are both in the same direction, so that work term is going to be positive 200 joules. Also, before I look at example 2, take note of the fact that this thing would be speeding up as it moved from left to right if this is the only force acting. So there's example 1. This 20 Newton force will do 200 joules of work as this object moves from position 1 to position 2. Alright, so what I'm going to do here now is I'm going to pause this and set up example 2. Alright folks, I'm back here, and we're going to look at basically the same example. This object is going to start here at position 1, and it's going to move over here to position 2, a distance of 10 meters, but it's going to do so under the action of 2 forces, a 20 Newton force to the right and a force I call F2 of 5 newtons to the left. Now what I'm going to do is calculate these individually. So the work done by F1, I'll just put a 1 here for the force produced by F1, is the same as it was in the previous example, 20 newtons times 10 meters, which is 200 Newton meters or 200 joules. And again, that work term is positive because the force is in the direction of motion. The work term by force 2. Now, force 2 has a magnitude of 5 newtons, and the distance is 10 meters. However, force 2 is in the opposite direction. The velocity of this particle is this way as it moves from 1 to 2. And force 2 is in the opposite direction, and that's the case where the work done is negative. So the work done by force 2 is going to be minus 5 newtons times 10 meters, which is going to be minus 50 joules. The net work is the total. Now, work is just a scalar quantity. It doesn't have a direction associated with it. It can be positive or negative depending on the force direction and the velocity direction, but it doesn't have a direction like a vector. It's not like when we add these, this term is positive, this one's negative, so we end up with 200 joules minus 50 joules, which is 150 joules. And again, this one is negative, not because this force points to the left, but because the displacement, the change in position, is to the right, and the force is in the opposite direction. If this object were to move this way 10 meters under this force, this force would be doing positive work, and this one would be doing negative work. So again, it isn't because of left and right, it's about the relative direction of the force compared to the displacement. And again, when a force is in the direction of motion, it does positive work. When it's in the opposite direction, it does negative work. So in this example, this force would do 200 joules of work. This force would do negative 50 joules of work. The net work is the sum of the two, which would be 150 joules. Also notice that this object would be speeding up as it moves from left to right. So I'm going to take a moment now and pause this and look at a third example. Alright folks, so I'm back here. I've changed my picture. Again, I'm going to call this example 3. This object starts here at position 1, moves to position 2, a distance of 10 meters, under the action of 4 forces. And I'm going to go ahead and talk about the work done by each of them and the net work done on the system. So the work done by force 1, I'm going to go ahead and call that work 1. And it's the same as it was before, 20 newtons times 10 meters, 200 Newton meter or 200 joules, either one. And again, that work is positive because the force is in the direction of motion. Work done by force 2 is the same as it was before. 5 newtons times 10 meters, except that work term is negative because the force is to the left and the object's moving to the right. That ends up being minus 50 joules. Work done by force 3. Now force 3 is this 10 Newton force directed straight up in the picture. That work term is 0 because force 3 is perpendicular to the change in position, or I'll say perpendicular to the velocity. Or we could say perpendicular to the change in position. Either one, because these are parallel. So basically this thing's moving to the right. This force makes a right angle, and again, only forces in the direction of motion do work. The work done by force 4, right, here's force 4, 10 newtons down, is also 0 for the same reason, F4, perpendicular to the motion. So again, whether you say it's perpendicular to the velocity or perpendicular to the change in position, or you just say perpendicular to the motion, these are basically all saying the same thing. Net work done in this example is still 150 joules, an important part of example 3. As this thing moves from right to left, the work done by this force and this force would be 0. Now, if this object were to move down, then this would be doing positive work, this one would be doing negative work, these two would not be doing work. So again, whether the force is positive or negative depends on the relative direction of the force versus the displacement vectors. All right, I think what I'll do here is do one more example. I'll call that example 4 and probably call it quits for this video. All right, folks, I'm back here and I'm ready to talk about example 4. This object moves from position 1 to position 2 under the action of 4 forces, F1 as it was before, F2 as it was before, F3. Now you notice I took off the magnitude of F3, and there's a reason why I did that. But then we got F4, 15 newtons at a 40-degree angle. So as this object moves from 1 to 2, and we're going to consider all forces here again, let's start with the work done by force 1. Same as it was before, 20 newtons times 10 meters, 200 joules, again positive. Work done by force 2, is going to be equal to 5 newtons times 10 meters, and that work term is negative for the same reason it was before. The force is to the left, but the displacement is to the right. So we get minus 50 joules out of that. Work done by force 3 is 0 because force 3 makes a right angle to the direction of motion. So it doesn't matter what the magnitude of force 3 is in this example. The work is 0 regardless. Work done by force 4. Okay, so now force 4 makes a 40-degree angle with the displacement. And remember that work is force times distance, but they have to be parallel. Whatever force you use and whatever distance you use, they have to be in the same direction. So to handle that, what I'm going to do is I'm going to take force 4 and I'm going to draw its vector components. Now, if you're in one of my classes where you're familiar with, we're using that terminology, vector components, that's fine. If you're in one of the classes where we're not generally talking about these two-dimensional problems, you can either keep watching the video or not. It won't hurt to watch it, but it may be, depending on the class, that we don't look at these types of problems. But all right, so this would be the component of force 1 that's in the direction of the displacement. Oops, I might have drawn that a little large here, but all right. Here is the component of, did I say force 1 too? I meant force 4. All right, so this red line right here, this is the component of force 4 that is perpendicular to the displacement. This one in red is the component of force 4 that is parallel to the displacement. When we calculate the work, we want to take the force component that's in the direction of motion. That's this one. And that's going to equal 15 times the cosine of 40 degrees. So this is going to be 15 newtons times the cosine of 40 degrees. So this product is the force component parallel to the motion. And we'll just multiply that by the 10 meters. And I'm going to get a calculator and get a number for that in a minute. But the one thing I point out is that that work term is in fact positive because that component points to the right and the displacement is to the right. And what we get out of that is 115 joules positive. And then in this example, the net work done, again, is the sum of these three, the algebraic sum. So 200 minus 50 plus 115 is, what does that end up being? 150, 265? 265 joules positive. Also take notice that this object would be speeding up as we go from 1 to 2. So I think I've hit about every case I can think of that's really important for now. Work is force times distance. The force has to be parallel to the distance. Forces in the direction of motion do positive work. Forces in the opposite direction of motion do negative work. Forces that make a right angle to the motion do not do work. If you have a force at an angle with the displacement, you break that force into components which are parallel to the displacement and perpendicular to the displacement. You use the parallel component of the force times the distance to calculate the work. So again, the purpose of this video is go through some work calculation examples. I hope this demonstrates pretty well how work is calculated. Have a great day.